Okay, first of all, so I'm thinking everyone can hear me just fine. I'm generally loud even when I don't have a mic. So we're going to be doing a small demo as part of this. So I have some things I'm going to hand out. Because I wasn't sure how big the room is, I'm not trying nothing, which means people are going to have to be friendly and cooperative with each other. So there are 2 envelopes, or 2 bags, and you need to work with the person next to you so that each of you gets one from each of the bags. So you and the person next to you are going to be partners. You will have one of both kinds. If you look really carefully, you'll see that some of the strips have a black line that's in the direction of the strip, and some of the strips have a black line that's perpendicular to the direction of the strip. So you and your partner want to have one of each. Does that sound good? Thank you. Okay, so while those are going around, so people who are coming in, I'd love it if you sat near the front, and I promise the social contract is, if you sit near the front, I won't take it personally if you have to leave early. But I think we'll let a few more people get settled and then I'll get started. Is there something else that's picking it up?
I don't know, have you got a phone in your pocket?
Yes. Let me have that too.
Yeah.
Perfect. Thank you. Okay. So I'm Debbie Chachra. I'm a professor of material science at Olin College on the other side of the ocean. I haven't actually been called young lady in a really long time. So today I'm going to be talking about 3D printing, but very much from the point of view of material scientists, which is what I do. And so thinking a little bit about the implications of the processes that we use, but also the products and the supply chains. Yes, right? So everyone in this room, I'm sure, has heard a bunch of stuff about the potential of 3D printing, and you may have seen sort of things like this. And actually, I'm just going to check. The people in the back, can you read this slide? Yeah. So I know there's been some issues with reading Brian. So the benefits of society is huge. No more shipping huge amounts of products around the world. No more shipping the broken products back. No more child labor. We'll be able to print food for hungry people. We'll be able to share not only a recipe, but the full meal. We'll be able to actually copy that floppy if you need one. So I'm going to kind of reality check this for a bit. So I said I'm a material scientist. So this is kind of what 3D printing food looks like. This is a chocolate printer. But actually getting to food to hungry people is really more about things like airdropping bags of rice. Right? It's not about the actual shape that it takes. It's about the material that it's made from. And so that's what we'll be talking a little bit about. There's 2 elements today I'm going to talk about. So one of them is why processing matters. So how you make things matters, not just what you're making it out of. And the second thing I'm going to talk about a bit is about closing the material loop. So processing matters first. So the last time I looked, it was hard to get an accurate number, but there's somewhat over 100 or so materials that are being commercially used for 3D printing right now. And there's new ones coming in all the time. This is actually a friend of mine, Megan Trainer, who was a PhD student at the University of Washington in Seattle, who was looking at a type of basically sintering glass. And so looking at a range of ceramics as sort of bringing a new material online. Mark Ganter, some of you may have heard of, as he's the person who reverse engineered a recipe to do 3D printing using protein powder and various other things. So it was like a sort of an expensive proprietary powder recipe, and he reverse engineered it to make it sort of cheap and open source. So this is the fundamental tenets of material science, which is that the material that you use, how it's processed, both affect the properties result from both what you start with and what you do to it, and the things you can do to it depend on both what the material is and what properties you're after. This is the central dogma of material science. This is like DNA to RNA to protein is to biology. This is to material science. So we almost never think about just materials per se. We always think about what are we trying to get out of them and how are we going to process to get those properties. So I have a very simple example to start. So how are we doing with the sample? Where are they? Raise your hand. Who has not gotten the sample yet? Most of you. Why don't we come back to this? I'm going to talk a little bit more and then we'll come back to this in a bit. So So instead of starting at the extreme low end of the demo, we're actually going to start at the higher end. So this is a 3D printed mandible, and it's made of sintered titanium. It was for a patient who had, I believe she had bone cancer, so her mandible had been removed, had been excised. And so they used modeling and then 3D printing to sinter a titanium mandible. And titanium is actually a material that's very commonly used for replacing bone. And then it was coated in hydroxyapatite, which is a mineral that's very similar to the mineral that's in bone, and was implanted. So my background is biological and biomedical materials, and so one of the first things you learn about biomedical materials is that they are incredibly sensitive to processing. So anything that you put in the body, the way it's been treated before you put it in, sensitively affects how the body responds to it. So a good example of this is the Bjork-Shiley convexo-concave heart valve. So this is a heart valve replacement. So this is when you have open heart surgery and one of the valves in your heart, there's 4 valves in your heart, would be removed and replaced. So typically, commonly things like rheumatic fever that causes it to get scarred, or they get blocked. So this is a synthetic heart valve made of synthetic materials that's used to replace it. Not sure how easily you can see it. This is pyrolytic carbon. It's like a special type of carbon that's extremely hard. There's struts that hold it in place that are made of titanium, and there's a sewing ring so that it can actually be sutured into place. And the disc basically tilts back and forth. So that's how it works as a valve. So when they first made these, this strut was spot welded into place, so spot welded onto the ring. And what they found was that basically the natural fluids of the body and the bloodstream were attacking that point of contact. And so the struts would fail, and this is a heart valve, so it had fatal complications. And because this is the United States, I believe the lawsuits are still ongoing. Excuse me. So they actually redesigned the process, and the redesign of the process was to actually just route out the shape out of basically the 3D routing, like CNC milling, out of a single piece of titanium, to basically avoid the changes to the material that happen at the point where it was spot welded. So this is, when I talk about the subtle effects in the body, this is the kind of thing I'm talking about. So when you think about, as I said, when you think about materials, there's applications where how we process them really, really matters. How are we doing for the strip of plastic? Who doesn't have a strip of plastic? So, okay. So this is a katana. And I just realized I'm not sure exactly when it's from. The thing that you can't see on this is actually a gorgeous sort of wavy pattern in the metal. So you could 3D print a katana with sub-micron precision, right? You can make something that looks exactly like a Japanese sword. It would have none of the properties of a Japanese sword, right? It's the actual processing, it's how you actually do the forging of this blade that literally rearranges the iron and the carbon atoms in it to have a particular structure that actually is what results in the particular set of mechanical properties that are in a katana. So we look at this and we're like, oh, this is what it looks like, but in fact, most of what makes it what it is all of the stuff that's internal, that's like the atomic level. And all of the sort of long, complicated, famous ritualistic forging processes are about getting that atomic structure right. So when we talk about 3D printing, what we're doing is we're saying we're going to take a space of the processing, we're going to take one type of processing, and we're going to create things with that. But from the point of view of a material scientist, what I say is, okay, if you have a material, you have this sort of huge space of properties that you can have, but if you restrict the type of processing we do to one type of processing, you're not actually going to be able to reach that whole space. And when more people have the plastic, I'll give you a little sort of hands-on demo of that. Having said that, of course, and the reason why, this is Neil Stephenson's book, The Diamond Age. How many people have read this book? Yeah, it's a lot of you. So this is a book about nanotechnology. And it's very much about doing nanotechnology from the atomic level on up, right? So this is where we can create materials that actually have this sort of atomic structure, that instead of processing it sort of the top down, we're going to put our sword on an anvil and bang on it. You can start thinking about processing from the bottom up to get the atomic structure we need. But this is kind of the level that we're talking about to have things that have the same sort of physical properties that for some applications are really important, right? It's important for most applications that are not, as Shapeway says, for decorative use only, right? For things that actually have good material properties. So at the moment, for example, 3D printed metal is relatively, it has fairly high strength and fairly high stiffness, but it still has very poor fatigue resistance. So if you're using it for anything that's moving over long periods of time, it doesn't survive very well. And obviously we're working on this. This is a moving target. Okay. I'm going to do one more check, I think, on the...
Nearly there.
Are we nearly there? So in that case, we'll do this before we move on. So you and your partner, so you're going to take your strip, and so we'll start with the lengthwise one. So I want you to hold it securely between your hands, and I should have cut one that I can demo it with.
Okay.
Oh, perfect. So basically the two strips are cut from a plastic carrier bag, like this, and the one that has, so it's basically, this one is crosswise, with the line that goes up and down, this one is lengthwise, right? So we're going to start with the lengthwise one. So you want to pay attention to your partner as they do this, if you're not the person doing it. Hold it between your thumbs, hold it sort of securely and evenly, and then pull on it until it breaks. And then think about sort of what it did. Now, take the one where the line is perpendicular to the lens, grab it, and do the same thing. Pull on it. Okay, so what do we notice? So which one is easier? This is what I have to do when you're doing a partner. Which one is easier to pull apart? Could you tell? The one that's perpendicular is a lot easier to pull apart. The one that was in the up-down direction was actually much stiffer, it deformed much less when you pulled on it. The one, the crosswise one, also necked, it basically extended a really long way. So when you make plastic bags, the way you make them is by basically stretching out the film in what ends up being the long direction of the bag. And so when you do that, the polyethylene molecule from that actually gets stretched out in that direction, so that when you pull on it, you're pulling more or less directly on the long polyethylene chains. Whereas when you pull it crosswise, you're basically pulling them apart. And it's much easier to pull them apart than it is to pull directly on those chains. So the reason why we did this as a demo is because plastic bags are like a metonym for like the cheapest disposable thing made of plastic. And even in plastic bags, we actually carefully do the processing and the design of the bag so that they're actually stronger and stiffer in the up and down direction, i.e. the direction that we're loading them in, right, when you fill a bag of groceries, versus in the crosswise direction. So even like the super cheap thing has this directionality, has this processing that helps them function. So like you could not, with current technology, you could not 3D print a plastic bag, right? Because it wouldn't actually have this structure. So this is why we want to think about processing. So, actually something, I just had this in remind me, something I'm actually really interested in is actually using 3D printing with other processes. So for example, 3D printing molds that you then cast. And so this is actually water-soluble 3D print filament from MakerBot that you could use to do things like that. But so one thing I'm sort of interested in is how do you get the benefits of 3D printing, like mass customization, but using them with other materials, other processing techniques, like casting, for example. So, the second thing I want to talk about today is about closing the materials loop. Is about the, you know, that thing we said, it's like they're like, oh, we are, let me go back and I'll show you. This idea of we'll be able to copy that floppy, no more shipping huge amounts of products around the world, no more shipping the broken products back, right? There's this whole idea that if you have a 3D printer, then you're sort of off the supply chain. That you can basically create things where you are and have them available to you. And of course, right now that is not true, right? If you do 3D printing with plastic filament, the plastic filament is at the end of a global supply chain around petroleum, right? So it is like you're totally on a supply chain. But we can do a thought experiment. Now the thought experiment is what would it take to actually take 3D printing off the grid, right? To actually have something that isn't attached to the supply chain. And there's a few ways you can think about how we might want to do it. So One thing we could do is we could use bioderived polymers. So if we could actually grow something locally and then use that to create polymers that we can then build things out of, we would have a sort of a local sustainable thing that wouldn't be out of supply chain. It would just be our field of corn, for example, that we were then using to make filament that we're then using for 3D printing, right? Not part of the supply chain. Another option is to use material that we already have in hand. And this looks completely invisible on the slide, but these are giant, this is a giant heap of palletized polyethylene PET soda bottles or water bottles, right? So huge amounts of waste plastic that are in our communities that if we could figure out how to repurpose that, we could basically use this to close the loop and make things out of. So at this point, you would probably have realized that when we start thinking about making things with local materials, we're kind of also thinking about making things with sustainable materials, right? So the things that are local are often the things that are reusable or are waste products that we can sort of close the loop on this. So this also means that we can think about, when we think about being off the supply chain, we can also think about what are some ways of 3D printing that we can make things sustainable. This is a pile of pellets for injection molding, not 3D printing, from a company called Preserve, which is based in Massachusetts, which is where I live. And they actually decided that they were going to make toothbrushes and now plates, like servingware, out of basically closed loop plastics. So when you buy, so they actually started by using yogurt containers, so polypropylene yogurt containers. But now when you buy a Preserve toothbrush, you use it for 6 to 8 weeks or how long you use your toothbrush for, and then you have to ship it back to them, and they grind it up, and they use it to make more toothbrushes. So very explicitly sort of closing the loop, and the same thing with the dishes. So it's sort of semi-disposable products, but they basically have built in a system to close the loop so that the plastic is actually reused to make more of their products. This is the Solar Cigarette project by Marcus Kaiser a couple of years ago. So this is a project that involves a Fresnel lens, so a large lens, to concentrate sunlight onto sand, and then to create sintered, to basically sinter the sand into objects. So this is using materials that are right there. So there's very local materials. And of course, my favorite example of getting off the supply chain is doing this in space. So this is an example of a company called V-Shape that's working with the European Space Agency to do 3D printing basically on the moon with lunar regolith. So the idea is that you just bring the binder with you, and then you actually 3D print a sort of soft, sort of dusty soil, probably not the right word, dust, I think it's basically dust, lunar regolith, on the moon to make things like space bases that are habitable. So this is totally, this is like out of the gravity well, totally off the supply chain, right? You're making things sort of right there with the materials that are handy. So, this is Ursula Franklin. Is there anyone in this room who has heard of Ursula Franklin? So she's one of my heroes. She is a professor emerita from my alma mater, which is the University of Toronto. She is a metallurgist by training. She started working in the field around 1950. She pretty much invented the field of archaeometry. But one of the things that she's best known for is giving a series of lectures, and it's now a book called The Real World of Technology. And I highly recommend this book and these ideas. It's about thinking about technology. But I'm specifically thinking about technology and culture. So in this book, she talks about prescriptive labor and holistic labor. So prescriptive labor is what we think about when we think about division of labor. So Adam Smith pin making, everybody makes a different component of it. These are Krispy Kreme donuts coming off an assembly line. Everyone has their own task that's involved. So prescriptive labor is when you're making sort of a large project which many people are involved in. It means that they need to be coordinated. This is an incredibly successful thing. In fact, so much so that we don't actually think about this as a thing, right? This is just like how you manufacture things. And it enables us to make things like Airbus 380s that we would never be able to make without the sort of large-scale coordination of lots of people doing their sort of assigned tasks. But we're also familiar with what's called holistic labor. And the image there is of a potter's wheel. And so holistic labor is what we think of as more artisanal labor, where the person who's actually making it is responsible for the entirety of what they're making. That they have an understanding of the whole process, they are doing the whole process, and they're making it. One of the things that I find really interesting about 3D printing is that we take something that is very traditionally and stereotypically prescriptive labor, things like injection molding, manufacturing, production, and we're actually moving it pretty much into the realm of holistic labor, right? It is possible for one person to conceive it, CAD up the model, and then do the actual 3D printing. But to me, part of the challenge of this is that now you are the person who is responsible for the externalities of what you're doing. So at this point, you can't just be like, okay, there's a factory somewhere, they're making this thing, they're doing something with the waste material, I don't know what it is, it's not my problem, right? You just sort of have prescriptive labor set up. When you're doing holistic labor, you are the person who's responsible for what you're doing, you're the person who's responsible for what's being produced and what's going to be waste and so forth. So I have kind of a challenge for people who are involved in this field, which is basically, so both on the processing piece, but especially on the thinking about materials, thinking about systems piece, we can do a lot better than we're doing. That's all I have to say today. Thank you.